Blagodurov, and I'm a PhD student in Simon Fraser University, all the way from Vancouver, British Columbia. And the work that I'm going to present to you this time is pretty much a key part of my research there, which was done under the supervision of Professor Alexander Fedorov. And the work is called User Level Scheduling on NUMA multicore systems on Linux. So at first, let's understand what pretty much NUMA systems are, because I guess maybe all of you understand what it is. So NUMA stands for Non-Uniform Memory Access Architecture, and in such these systems look something like you see on this slide. So here you see AMD Opteron 8356 Barcelona processor. The latest processors from Intel, from Nahalem architecture, they look something like that. Their previous processors, Intel Xeon, they had quite different architecture, but they sort of like a bar a lot like this from AMD recently. So Nahalem looks more or less like what you see here. So for Barcelona, depends on the particular server model, you can have either 4 or 6 cores per socket these days, and typically each core will have level 1 and level 2 caches as product for its own use. Then there is also the third level cache, which is shared across all the cores in the chip. Its size depends on the amount of the number of cores that you have on the socket. If it's 4 cores, it's usually 4 megabytes. If it's 6 cores, it's usually 6. Whereas for private caches, the level 1 a few kilobytes, maybe 64 or something like that. The level 2 cache usually holds a megabyte. But the last level cache is significantly larger than the first two. Then there's instruction on the core, which executes on the core access of data, and it cannot find it in any of the caches. Then it goes all the way down through system request interface and crossbar to main memory. So the main memory of the non-uniform memory systems, it is spread physically across the entire system. It's not located in one place. So it can be either local, so it's situated locally on this node, and this is on memory node 0, which is pretty much the memory chunk. Or it can be on some other sockets on the system, in which case the access will go through hypertransfer controller to other nodes on this multicore server. So this particular configuration has 4 sockets on it. This is what I don't remember the server model, but because it really ships. I mean, HP and Dell ships this kind of server models quite frequently. It's one of their most popular server configuration. It will have 4 sockets on it, and every socket will have its own memory bank there, right? So within the socket, you already know what's in there, but they are connected through this network within the server, and this network usually is not symmetric. So you see how all of them, 2 of the chips, two of the nodes, the NUMA domain 1 and 2, they're connected to 3 links for the rest of the nodes, right? The NUMA domain 0 and 3, they're connected only to 2 links. The missing link is used by AMD to do different stuff, input-output related stuff from the storage. So because of that, it usually can be not symmetric. Some of the servers, they will have not 4 sockets, but even more than that. Can have up to 8 sockets these days. And it is expected that this number will increase with the time. So let's say that we have this NUMA server, which is pretty much most of the servers that HP and Dell ships these days. And let's say you install Linux on it, which is pretty much mostly, I guess, the most popular server operating systems these days. So you install Linux. You have maybe the latest kernel version. We used in this experiments to 16.9, but the same will hold for the latest versions to 16.37 or 38 as well. Let's say you install Linux on it, and let's say you ended up by running several applications. Some of them started earlier, some of them finished by that time. Let's say you ended up with the configuration that you see on this slide. So we have 2 threads executed on the cores in the NUMA node 0, thread A and thread E. And they're all accessing memory locally on the node, right? Memory is nicely located in one place. And in this case, they will have the connection for memory controller, because they too will access the memory from the same memory node, but memory controller will be shared among them. So because of that, they will compete for that, and they can experience performance degradation due to this competition, if they both will use the memory frequently. So what the default Linux scheduler will do is that it will try to preserve the load balance in the system, right? It can migrate the thread B on the different socket, let's say, right? So in this case, the load balance will be preserved, but by default in Linux, memory is not migrated, right? The Linux, it has a principle local node first, which means that the memory is allocated locally for the thread at that particular point of time. So let's say we have the memory page, which application requests at that particular moment of time from the storage, it will be allocated naturally on the node closest to the thread at this particular moment of execution, right? For thread B, it will always be the memory node 0. For thread A, in the initial stage, let's say of experiment, it will be also memory node 0. But after migration, memory will be started to Linux will start allocating memory on the new node, right? But the old memory will stay on the old node. It won't be migrated along with the application. And this is just sort of the data to prove that. So here you have, I took one of the applications from scientific applications from physics. It simulates some thermodynamic processes there. It's called milk. And in this experiment, the application was spawned on one of the cores adjacent to NUMA memory domain 0, and then at the middle of the execution, it was migrated to memory node 1. So the memory, the amount of memory total residence at size for the application in megabytes on the memory node 0 is given as a red line, on memory node 1 is given as a green line. So as you can see, a lot of applications, especially those that are CPU intensive, they allocate most of its memory in the first maybe a few seconds or minutes of its execution. So as a result, you can see that at the first, in the beginning of the execution, there is no memory allocated on the memory node 1, right? This application is not run in there. But it's most of the memory is located on the node local to application in the initial stage of the execution. Then after that, the majority of the memory allocated to the memory node 0. But then it just uses it, works in its working set during this execution. Sometimes it can allocate more pages, sometimes it will release some of the memory pages, and the total residence size will be lower, but it will be more or less on the same level. So after migration, supposedly to preserve the load balance, we will, the thread will also continue to allocate memory, this time on the new node, but the rest, most of the memory will stay on the old node. So if the application accesses its memory a lot, it will be prone to remote access levels, right? It will access memory on the remote node, and because of that, it will also have the performance degradation. So just the completely first scheduler that is sort of like the scheduler is based for Linux. What it does, I guess the breakers were aware of that. The way it addresses right now is just, well, it tries to migrate the threads less frequently between the NUMA domains. So you have the NUMA server, and you have the Linux installed on it. You can, usually the way Linux is installed on NUMA servers, so that you have the option NUMA support, turn on NUMA support in kernel. You can turn on this option, and scheduler will sort of like determine how many memory nodes there is in the system, and it will associate with every NUMA memory node a concept which is called scheduling domain. So what it does is that every scheduling domain will be associated with every NUMA memory node in the system. And when the scheduler will try to preserve the load balance, it will consider the cores within the node rather than the cores outside the node. So certain events, for example, if you have the context switch, this is usually the good time for a scheduler to check if the thread should be migrated to preserve the load balance. So when it analyzes what cores the thread can be migrated on, do you have some question? No? So the thread will be migrated on, it will only take into account the cores in the same memory node. The cores on the other nodes will be masked. The thread will not be migrated to them. So it will definitely improve memory locality, but sometimes it could result in contention for memory hierarchy of the machine. When, for example, you have two more memory-intensive threads, so like stuck on the same memory node. So just to recap, so you have two threads, let's say they will access the memory often, they're CPU intensive, and if they are running on the same node, I mean, they will experience the contention for all the shared resources there. They will experience contention for shared level cache, for memory controller, and if you migrate the thread, the memory controller contention will still be there unless you migrate the memory alongside. So to prevent this performance degradation, which can be actually as serious as twice as slow in comparison with the solar output application on the idle machine. To prevent this contention, we need to detect the amount of memory intensiveness of the application, right? We need to detect if we have two threads A and B, how memory intensive they are. So for that, this is sort of like a common knowledge in systems research field and computer science. So we in our lab published quite a number of papers actually on this case, and Intel published quite a number of papers. So it's sort of like a common knowledge these days that the last level cache miss rate can be used to detect memory intensive threads. In reality, it's a little bit more complicated than that. There are a few downsides there, but this is a good sort of metric to tell how memory intensive the thread is. And what miss rate is the number of last level cache misses. In this case, misses from the level 3 cache per retired instruction on the core, per thread. If the value of this last level cache miss rate is high, then the thread is memory intensive, right? And then what we can do to prevent memory hierarchy contention in this case? What we can do is that we can identify memory intensive threads with this last level cache miss rate value. We can spread them onto different memory domains, and we can migrate the memory alongside. Right? So for example, so we have these two threads competing for shared resources on the memory node. We migrate one of the threads on the different node, and we also migrate the memory alongside. So in this case, all of this performance bottlenecks will be hopefully manipulated. So this is sort of just to give you a flavor of what kind of scheduling algorithm can be used to solve this problem on the NUMA system. This is one particular problem, right? Scheduling problem, just to reduce the amount of shared resource contention on the system. In general, you can, you can have different problems there. Depending on your area and what you're targeting at, you can, for example, will maybe want to try to improve input-output performance of the application, or I don't know, try to schedule them in time rather than in space. So you will try to maybe hold some application, then execute another one, and then restart the first one or something like that. But in general, the point is that scheduling these days on Linux can not only be done in kernel, right, as it usually is. Completely fair scheduler is implemented purely in kernel. But these days, Linux provides all of the opportunities for you to schedule on user level. And by scheduling, I mean, usually it means assigning threads to cores. So for example, if you have some time interval and you have, let's say, 8 threads executed on the system, you need to break this interval into tiny parts, and then you need to decide in which scheduling interval what cores should be running what thread. So that's the scheduling process. On NUMA system, it's more complicated than that. You need to also consider where the memory of each thread will be located in every point of time. That's sort of like the main problem on NUMA system, main challenge, right? And why scheduling in user level is interesting these days, right? So first of all, in HPC domain, the way schedulers work is that the cluster scheduler, it is usually installed on user level because it's just simpler to maintain. All you need to do is just to run this daemon on every cluster node on user level, and you don't have to worry about a particular kernel version of a particular scheduler there. You just install it and it works. And then you cannot necessarily cluster, you can have different operating systems, and we hear yesterday read a really good presentation about virtual framework and clusters. It also kind of tries to target different maybe architectures, different operating systems on the cluster. And another big concern these days is user level applications these days. They will maybe want to schedule their threads, and they may be, because of they have the application specific data, right? They know what their threads doing. They can schedule them better than by default Linux scheduler, right? Because default Linux scheduler maybe looks at certain things, CPU intensiveness, the number of scheduling intervals, scheduling ticks, this particular thread width and view CPU to be scheduled or something like that. The application generally knows better what threads is more important to it, how it can prioritize threads, and by that it can supposedly achieve your performance. And because of that, because application can schedule its threads better, it wants to be able to do that, right? It needs some kind of opportunities to tell that I don't really want this thread to be scheduled by the default schedule. I want it to schedule by myself. Then this is sort of the feature that is supported by a lot of programming languages and programming libraries. So to name a few, OpenMP supports it, Silk supports it, Intel Threading, Building Block supports it. The reason why it's so popular these days, why people are talking about this stuff, is because, well, it's pretty much the same reason why we have a lot of cores on the servers these days, right? So before, if you look, well, on the server market, it also holds them. For example, on desktop, in the previous times you just had, if you look at the Pentium 2, Pentium 3, they all had more or less the same, one core, right? But it's just, it was faster at the time. With every single generation, it was faster. These days, because of several walls that have been implicated in the current technology process, the cores cannot get any faster, right? There is memory wall, energy wall, cooling wall. They cannot get any faster. But since AMD law still holds, and in every new processor generation, they get more and more transistors to use. Instead of using them to create one bigger, faster core, because they cannot do that these days, they create several cores relatively of the same performance, but with every processor generation, there will be more of them. So before, for example, you had one single core, then you had dual system. At the time, maybe 2001, 2002. Then it became 4, 8 cores, 16 cores. These days it's, these days it's actually 32 cores, but it will be 64 just really shortly. And then it's expected to increase 128 to 256 and so on. So while performance of every single core is not expected to increase by much, the number of these cores will increase dramatically in geometrical progression pretty much. So because of that, instead of before you didn't really have to worry about parallelism, right? You can just create your program and you can buy the new processor, for example, Pentium 3, and it will run faster because it's just the processor is faster. These days, if you want to take advantage of the new processor, you have to parallelize the application. You should be able to run your application with 800, let's say, 28 threads. Then in this case, you will take advantage of the multicore system. If you get the next model, if you want to take advantage of it, it's not just simply enough to buy the processor. You need to parallelize it again. You need to parallelize it more, so you will be able to run it with 256 threads. So all of these opportunities, namely, for example, Intel Threading block, building blocks, and stuff like that, they are there to ease your job of parallelizing because it's usually quite hard. And user level naturally comes here, since applications again will want to maybe parallelize their applications and maybe want to prioritize certain threads. And it is generally the applications themselves can do better than the default Linux scheduler, right? So in order to schedule applications on user level, what do we need to do for that, right? Well, we need some kind of monitoring features, right, from Linux. We need to know. We need Linux to provide information to make the right scheduling decision. We need to monitor the threads. We need to tell what are their characteristics besides application-specific data, right? And we need to get it online as applications execute to take into account for phase awareness and something like that. That's important, right? Another group of features are called action features. They allow us to make the right scheduling decisions. Once we have all the necessary data to make the right scheduling decision, then we make the scheduling decision, then we need to enforce it, right? Then we need to tell the Linux, okay, I want this thread to run on this course, and I want to actually run it now. So you need some kind of functions to do that. Just to recap, so in terms of monitoring features, Linux provides pretty much everything that is necessary for that, right? So for example, information about core layout and memory hierarchy is accessible via this file system. At least it was on 2629, but on the latest kernels it's also you can also get this data maybe a little bit differently, but still from some sort of file system. So you can get what core IDs are sharing the same memory node, what core IDs are sharing the same cache, right? What is the size of the cache and stuff like that from just by reading special system files, right? And all of the information you can get it from there on user level. And for example, which cores share every NUMA memory node in the system again? In process 99.6 file system. Which core ID if the given thread is currently running on? From proc file system, it's easily obtained. You just parse the start file. It will tell you what core the threads is running on this particular moment of time. Detection of multi-threaded applications. So multi-threaded applications is like, so you have several threads of execution, but let's say you want all of these threads sharing the same memory footprint of the system. So these are what multi-threaded applications are. It is important to detect them. For example, scheduler that don't have, let's say, application-specific data. So it can possibly schedule the threads in the same memory node because they're sharing memory. So you will naturally want them to be closer together so that there will be no memory spread because you don't know upfront what part of memory each thread will be using. So you will want to detect. And it's also quite easy to do. You can just parse this file from again proc file system, stack this file, and it will give you the thread group ID. And the challenge with multi-thread applications is that Linux generally it doesn't really, in terms of process scheduling, it doesn't really distinguishes that much between the thread and the process. So the process is pretty much the entity that have its own memory footprint. Thread can share the memory footprint again with several different threads. But in terms of scheduling, right, there is not really that much of a difference. It's all scheduled the same. If you want to schedule them differently, if you want to schedule multi-thread applications differently on user level, you need to additionally detect what threads are sharing the same memory footprint. And for that, you can use this file. Memory stored on each NUMA node for the application can be also accessed on proc file system with NUMA maps. You just have to break down per memory page for every memory node in the system for every memory footprint, right? So it's also quite easy to do. And then detection of, depending on what applications are your target, my research is targeting compute-bound applications, and those that actually do some computational work, those that don't wait for the data to be brought from storage into main memory most of the time, or through network to memory. And because of that goal, you can naturally detect the compute-bound applications via top. You can run it in batch mode, and it will give you the output per interval of time. You can parse this output from the pipe, for example, and then get your information. Then also you can get it from GIFs. So GIFs is like a small interval of time, something like scheduler GIF. You can get this information. So what amount of work that this core actually did for this thread from this file, again, a profile system by parsing the certain columns there, 13 and 14. You can get all the details from the paper. It's really general level stuff to get up to speed with that. So then detection of input to output bound threads. There is also application on user level, which is what I am talking about installed on Linux. And what it will give you, pretty much the output similar to top, but it will give you the amount of traffic per process.
I think there's also a way to use the NUMA CTL or the NUMA.
That is true. Yeah, there are different ways to do that. So yeah. I think I mentioned.
I think these NUMA CTL sometimes takes from these, but some of the things they test for by itself. If you look at how the RPM itself works.
Fair point, fair point. I actually mentioned it in the paper. So there are, for all of this, there are several ways to do it. The way that you will prefer depends on your application. You can read the system files. You can install the special user level package, which is called NUMA CTL. And what it does is that it will use certain parts of the files as well, but it will give you, maybe it will use some other, I'm not sure really, but it's possible. It will use some kind of diagnosis features, and it will give you the input in the nice form, right? So you can parse the output of the NUMA CTL rather than to read this file directly.
How often do you read this information?
Depends on how often you want your schedule to threads to be scheduled, right? In my algorithms, I usually find it worthwhile to schedule every, let's say, 2 seconds. So yeah, for example, it will depend on the application on your purpose, but generally I don't really see the reason for NUMA system. When you migrate the memory, it takes a lot of time. On NUMA, on Linux, on NUMA systems, I read quite a number of papers. There were enhancements in terms of memory migration, right? Because when you migrate the memory, you want to migrate all this data. It's expensive operation. It takes a while to migrate this data. It consumes the network and stuff like that. But generally, there were quite a number of enhancements in Linux, and it's quite efficient these days, but still, it's quite expensive operations. Because of that, you don't want to have the scheduling iteration in the millisecond range, for example, because you want to get a lot of performance.
The next question, are you getting to present a sort of mathematical problem or formulas that you are going to solve this problem?
Oh, I solved actually this problem. I will talk about it a little bit later. But the point is, this paper is about the scheduler application, right? So for Linux, maybe what you're asking is research, right? I'm just intentionally.
Not research, but you have to use sort of a formula what to do with this.
Yeah. I know what to do with this. So I'm just presenting how to do that because, again, my research is considered dealing with computational intensive applications, not the scientific, right? So my research is really targeted, but I'm just talking to you how you can schedule threads and user level in general, right? You might have completely different rules. I know how to schedule my particular part. I will talk about it in a few moments, but generally, this it's interesting problem. It's interesting to me, insanely interesting because I'm a researcher and stuff like that. But this paper is not about so much this particular scheduling algorithm. It's about how you can do user level scheduling in general, right? So, but my advice on NUMA system is that generally you don't want to schedule in a millisecond range the way completely prepared scheduler does, because again, completely prepared scheduler deals with it doesn't migrate the memory because of that. So all of these NUMA effects you want to target maybe seconds, scales, something like that. In clusters, schedulers normally have several minutes iteration. So because the jobs there are running several days, maybe several weeks, so they don't want, even seconds for let's say HPC clusters is a lot. It's too small, I guess, to find a rate. They will want to have the scheduling interval of minutes or something like that.
Excuse me.
Yeah.
As far as I understand, the motivation for migrating memory would be if the pages used by a single process or by some process are spread over different memory zones. Okay. So the question is, wouldn't it be possible to avoid the pages of a process being spread over different nodes, and that would make it unnecessary to migrate memory, and in that case you would only have to schedule the process on the node that is close to the memory.
Fair point, but then the problem is, if you have the static or both, then yes, it's possible. So let's say you start applications and then you run them to completion, for example, right? So in this case, if no applications will come and go, you can just assign them to this particular memory node. You can leave the memory there, and you'll be happy with that. But the problem is, just consider the case when some applications will finish, let's say, right? So in the example that I showed you, there were 2 threads in the system, right? Just imagine that several minutes before that, there were 16 threads in the system, and some of them just finished, right? And then there were 2 threads left. So we cannot predict the future. We don't know how many threads will be run in the next, for example, few minutes. So the best we can do, we need to use the information that we have. The best schedule precision up to that point for these 2 threads is to might spread them apart, right? But the memory, again, all these problems with the memory. If you're certain like scheduling problem, right? If you have that with application-specific data, and you know that, that's fine that I have 2 threads right now. I will not schedule more than 2 threads in the near future. In this case, you can leave them on one memory circuit. If they don't compete, that's fine. But then the problem is, generally about scheduling problems, we don't know what will happen next. So because of that, we need to migrate. Because sometimes it may be the efficient solution if you consider this particular information, up to now. Do you understand?
Sort of, but
it depends. It's just in these dynamic conditions where the workload, where the applications come and go, you just sometimes you might have to do it because it's the most efficient solution up to now. And if you don't know the future, not much you can do. Again, actually, this is a little bit more interesting. Maybe I spend more time on that. So this is action features, right? So these are monitoring features. You can get information about the workload. These are action features that are provided by the scan everything that you need for information. If you guys are interested in this slides, I can just give it to you. You look up like folder every single one of them. So, for example, thread binding, right? So if you want to bind the threads to the course, very easily done. There is a user level application which is called toolset. There is a special system kernel system call which is called set affinity. All of them will do more or less the same. You get them, you will provide them with the CPU mask, and then the thread will run only on course from this mask. How the thread will run on the course from this mask will generally be determined by the default schedule, right? But if you don't want the default schedule to be interleaved in any way in your schedule, you can just, schedule every thread individually. You can just specify the mask from one core, and in this case, it will run only on those core. But if you want to sort of, ease your task, you can just specify, okay, so this thread will run from core 2, 3, and 5. And how they run there will be determined by the default schedule. Then the point about memory migration. So Linux provides the opportunities for course grade migration, NUMA migrate pages, system call on migrate pages too. All of them will migrate all of the pages for the given process ID or for all of the threads of the same multi-thread application because they share the memory footprint from one node to another. All of them, all of the pages. It can be several gigabytes, for example. So that's why it's called course grade migration. Fine grained migration is where you have NUMA move pages system call for that. And what it does is that allows to specify logical addresses of the pages that have to be moved, which is useful when migrating hot pages. So the pages that are accessed frequently, you don't want them to be accessed remotely on the different memory nodes. You want them to be accessed locally. So because of that, you use the system call. If you know the logical addresses of the pages, you will migrate them. This is fine grained migration, as fine as it can get. So the granularity is the size of the page. You can get huge pages and stuff like that, but default is 4 kilobytes. And then there is automatic page migration. So this actually, I don't know, I quite like this feature. The Linux kernel since version 2.6 it supports CPU sets mechanism. Maybe some of you are aware of that. So what it does is that it migrates memory of the application to CPU set changes. So let's say you have this application, you say this application will run only on this course, but the difference between this CPU set mechanism and the task set is that it's more sort of convenient for you. So you can just, let's say your application will run on course 2, 6, and 7, and then after that, okay, I will change the CPU set, it will run only on 6 and 7. And then if some memory will be allocated on the memory node local to core 2, which you remove from the CPU set in the later point in time. Then this memory will be automatically moved to the memory nodes for which the core 6 and 7 will be adjusted. So this is sort of like ease your job in a way. Then Lee, I believe I spelled his last name correctly, Schremer for it. What he did is that he further extended this CPU set functionality. So his patches, if enabled, migrate the memory along with the thread upon its migration. So from I've read the kernel development forums. He contributed quite a lot of stuff. I guess maybe some of you are aware of him. So he contributed quite a lot of stuff to this. And well, he devised these patches. It's not a part of the official kernel tree. If you're interested in this automatic migration, you've got to install them separately. But from what I can tell, they're quite effective. My experiments tell me that the memory is migrated efficiently, and the good part about this is that this automatic page migration, because his patches at the network, they migrate the memory along with the thread upon its migration to another node. So before on the CPU set, the memory will be migrated only if you explicitly change the CPUs on which this processor will run, right? What he did is that if you have, again, the CPU set for this application or for the number of applications, right? And they still have the cores 2, 6, and 7, and then the second interval, they continue to have cores 2, 6, and 7. But then, for example, for some reason, you decide to migrate the thread from the different core by yourself, not by changing the CPU set, but just, rebinding it. And in this case, it will automatically detect, again, that the thread will be migrated and migrate the memory alongside. But how memory will be migrated, it is dependent. The patches, they can migrate the entire memory, or they can migrate only part of the memory, only hot pages. So this is good because there is no spikes in utilization of the network, right? Some of the applications, for example, that are CPU intensive, they have, let's say, several gigabytes of the memory footprint. You cannot migrate it towards grainly because it will just sort of like the bus will be filled up because all of these pages they're trying to migrate it and the bus is not endless. So what you want to do is you want to migrate on the pages that are actively accessed and then just migrate it based on touch, right? So you touch this page, maybe first request for this page will be removed, but then it will migrate this particular page after the first access to the local node, and then all of the rest of the access to this page will be also local node. So this allows you to spread sort of this memory migration burden within the time, so it won't be as sharp, like by and I guess it on Linux 2636.
Is this a part of the scheduling scheme, or is it inside the context of the process itself?
It's just a part of kernel. You just can't.
No, what I mean is it's a part of the kernel, but when you run in a kernel, you can run in a generic kernel thread that does the operation, or is it, or like when you have problems with, for instance, I/O. You have I/O sometimes when you don't have enough I/O. When you want to allocate memory sometime, then you get to some state in the kernel where the process that runs it itself frees some memory. The question is this done as something like kswapd or bdflash, as something generic? Is it done all the time? Or does the process do it itself when it starts to work?
It does it all the time.
So it's a kernel thread that does this all the time?
I'm not sure about the particular thread, what it does. I don't know what dispatches do exclusively, and ask me about it, right? I'm like a user for them, right? Just like I'm a user for top.
Okay.
I just use all these building blocks that Linux provides to me, and I solve my problems there, my scheduling problems. I don't have to worry about, for example, how top is implemented.
No, yeah, but...
the same here. So I just patch the kernel with dispatches like you patch the kernel to use Zen, for example, right, or whatever. And then you can just use that. I'm not sure how they implement it inside. Maybe they're implemented with the existing kernel thread. I don't know. I know the guy whom you can contact and ask, right? I'm running on the thread, so really quickly. So this is about how you monitor the threads and how you bind them, right? So sometimes the information that you have from the kernel, for example, on what cores the threads are running, and what kind of, what is the amount of memory that is being located on every member node. Sometimes it's not enough, right? Sometimes you just need to know more about the threads in order to properly schedule them. So yesterday there was a presentation about these traces, the log files, and it will give you the detailed information if you put the trace points in specific parts of the kernel. So one of the sort of like opportunities there were hardware performance counters, right? I'm sorry? So one of the opportunities in your work were hardware performance counters, right? You can monitor them. So this is like, your work is more like complicated than mine. So I just monitor hardware performance counters because I know what I want from them, right? So the point is that there are hundreds of events that you can possibly monitor. In Intel and AMD, they have, I don't know, even more than that actually. All sorts of factors in the architecture. You monitor events in the input-output sort of chain. You can get the events from the cache, you can get the events from memory controller, anything you want pretty much. You just specify what event you want, and then it will monitor with this hardware performance counters, which are pretty much the registers in the processor. So if you want to compare any overhead to you, it will just be there, and you just can't read them, right? Periodically. For example, if you're interested, I personally interested in less level cache miss rate, what I can do is that I can just tell performance monitoring unit, so I want to monitor less level cache misses, and I want to monitor retirement instructions on every core. And then it will give me the updated information for both of them, and then I can just read them without any performance overhead on the system. And since I'm interested in less level cache miss rate, I can get it quite fast and efficiently with this performance counters. So yeah. operating systems, it was only that, right? The number of events that you can monitor is increased with every, subsequent processor model. I found that on Intel, generally, it's a little bit, better because not as much events are bugged. Because sometimes you can just think, okay, I'm really interested in this event, but if you, for example, you see that they don't really make any sense when you monitor them. So you contact, for example, architects, they say, yeah, it doesn't really work as it's supposed to. So because it depends on the implementation, and sometimes the implementation is not as good for processors and stuff like that. But generally, I found that the Intel is a little bit more sort of debugged. But AMD is cheaper, right? You can get like one AMD server for the price of two AMD servers for the price of one Intel server. And but these days on the modern processors, on the and 980s, you get these modules work in two modes. So first mode is the traditional one. You can profile only a small set of particular events, but for many instructions, right? Let's say you have thread executed on core, and it has like several, within the several seconds it will be like several billions of instructions easily returned, right? And if you want to know the less level cache miss rate, you can get the number of less level cache misses, right? Within these several seconds of execution, it will be like several hundreds of thousands or something like that, or several billions of returned instructions, right? But you won't be able to tell what instructions missed in the cache. So you will get this limited information, in this case less level cache misses, but you won't be able to tell which instructions precisely missed. The second mode, it works differently, right? Precisely, just vice versa, right? It just will give you very detailed information about a particular instruction, but the number of thus profiled instructions is really limited. So let's say among this billion instruction, you will get maybe several of them, maybe like 10 or 20. Depends on the frequency that you set up. You can get as much as like several hundreds of them profiled that way. But these stacked instructions for them, their number is really low, but you can get all sorts of information about how they behave, for example, in memory hierarchy of the machine. One of the data that you can get from there is the logical address of the page that is. So with this logical address, you can, for example, detect the hot pages and try to migrate them this way. It's not the only way that you can migrate the hot pages. As I said, for example, we implemented this special speed up in kernel. But for example, this can also be used in a way to migrate memory partially to migrate on the pages that are hot. Yeah, and I don't have time for the second mode. Everything, all of the details in my paper, all of the links to the kernel, to the processor documentation, you can read about it. You can read the register specifications to access and how to access it. It's in the paper. Here I just try to provide a general idea. So the first mode, let's say you want to, in my case, I want to, let's say we have the last level cache miss rate. For that, I want to use the hardware counters in the first mode. And, well, I can read the registers directly, right? I can just access these registers. If I have the necessary permissions on user level, it's possible to access them. Because there are special sort of registers in processor which can be accessed from user level by definition. It's like these registers are from user space, so you can access it. But generally, it's easier to have to use the software that already does it for you. So you just specify the event, and you just within this program, and it will just give you the output of this counter, so you don't have to access the raw registers for that. So this is quite convenient. One of the John Masters yesterday told about it. So basically, whether we in perf these days you can access the events. There is like some pre-configured events in perf, and you need to. I personally find that perf is the best for kernel version higher than 2629. You can use different tools. You can use all-profile. It will also does more or less the same thing. You can use API. This is the library that also profiles the performance standards. But I personally like perfmon before kernel 2699 and perf because it's official tool after all since version 2629. And there was a discussion yesterday. So John Masters mentioned that well in perf there is not really a predefined events. So the interface that it provides that you can access through the registers, but there's no real this convenient interface that tells, okay, I just want to access level allocation uses. I don't care if it's on this particular architecture, if it's level 3 or level 2 or whatever. I just perf, it's generally, well, in perf, it is possible to obtain certain events that way, like irrespective from the architecture, but generally most of the events which you're usually interested in, there can be only accessed from raw registers. Perf1 is more sort of, it's better in this respect. It's older tool than perf, so it's more sort of well thought, I guess. But the creator of this program, he said that Stefan Iranian, he said that he will not support this tool because there is perf, there is official, profiling tool within the Linux and the version 2629, and he supports perf these days. But still, in my opinion, it has a little bit less features than perf1. But I think if you take a look at every new kernel version, the opportunities in perf are increasing. So it has more and more opportunities with every single kernel version, so we'll expect it to catch up with the very soon. Generally, any tool pretty much for scale that monitors the hardware counters is applicable for scheduling purposes. It only needs to provide you detailed description of processor's input capabilities, or you can use docs if you're just lazy, right? It needs to have the counter multiplexing. What it does is that the number of hardware registers are limited that can give you the information you need. So if you have a lot of threads, this register usually it's the number of 2 to 4 registers that can track the information at the same time. So if you have a lot of events, you just need to have sort of more points of monitoring than this number of registers. So what perf and this one can do is that multiplex. So it can use the same register at different points of time to monitor different events or for example for different threads. In this case, you will get the necessary information for every thread. It won't be as precise as without multiplexing, but that way you can monitor more threads or more events for each. Then a periodic output of intermediate number of events, you need to have it in order to schedule online as applications execute. And it will usually require catching the perf. But perf is just specified as we want it. You just need to turn on perf events and you need to install the package and it will work. Yeah, I don't have the time to give you like a small tutorial. So here basically I wanted to just walk you through, just use NUMA's field package, determine the layout of the cores, and then determine the description of the events with perf1 in this case. And then just give you the information. But you can read it. If you're interested, you can read it in the paper. Everything there is presented. And then this is the information about the last level cache misses. So this is, it has, even within every event, you can configure them differently. So for example, for last level cache misses, you can monitor different misses that appear. You can read block check, with block modify misses, kind of. You can monitor them for different cores and stuff. So you gotta kind of choose what you need there, but all of these opportunities are there. This time they're only accessed by Linux, but they're provided by this CPU architecture. This is sort of like a limitation, so you gotta be aware of the limitations of every architecture. For example, if retard instructions can be accessed per every core, so you can get a different number of retard instructions per each core. With less level cache misses, naturally they're accessed on the socket level, right? Because the cache is shared. But if you want to start several monitoring sessions, this is straightforward for you. You just want to start one session per thread, each of which is determines last level cache misses rate. On AMD, you won't be able to do it because there are hardware limitations. You just need to profile all the last level cache misses for all the cores in the chip from only a single core of the chip. So I have details in the paper. You just need to be aware of that, and you just sometimes need to read the documentation because tools, for example, perf1 and perf, they will not be aware of this like time and rate limitations there. They are, you can still use them, but there are sort of details, right? So you need to just schedule them in a certain way to get the information you need. This is how you invoke perf1. So you invoke 2 sessions, profiling sessions per socket. One session will monitor all of the retard instructions for every core. The second will monitor all of the last level cache misses from every single one core of the chip, for example. And this is the same with perf. Again, with perf1, you see like there are description, nice titles for the last level cache misses and stuff. So for perf, you need to access this register directly because there is no way, for example, to tell that I want just last level cache misses. You you need to specify the accesses to registers for that. Very briefly, so all of this data you can get it from Linux documentation easily. I have it already done, so I spent quite a number of time on debugging it and adding different features. So I have this scheduler there with which I perform the test. Right, I test different scheduling algorithms, what can work, what cannot. I have this program. It's really simple. It's written in C. It's not really that big. It's about 6,000 lines of code, something like that. It's really small. So, and it's released, right? I released this in open source. You can get it. You can use it wherever you want. And if you have any questions, just feel free to ask. You can use it as a if you have some kind of application-specific requirements, you want to schedule your threads in user level, you can maybe use it as a starting point and then go from there. It has three main phases of execution. Preparation, where it starts the supporting programs in batch mode and starts the parsing threads. So basically, for example, if you want to detect the input output on threads, you need to start at the top in that. For example, the information you need to parse this output and stuff like that. And and then you can either start a workload that you're interested from the configuration file and specify what applications you will run at one point in time. Or, for example, it can also detect the application. Since on user level, you don't want to schedule every single thread in the system because most of the threads, there are daemon threads, right? They don't really do anything, they just wait there. They can easily be scheduled and handled by the complete repair scheduler. With user level, you want only schedule threads that really matter for you. It can be CPU-intensive threads, it can be input-output-intensive threads, any threads that is useful, right? So you're just interested in only subset of these threads. And in order to detect them, you need to have some kind of threshold. For example, if you're interested in input-output bound threads, you can say, okay, I want to detect only the threads that have the input-output bound at some point in time, for example, 195 per second for the storage, right? And then you only single out these threads, and you only work with them, right? It will detect only these threads and not anything else. So the scheduler allows you to do that. Some logs the scheduler holds, I will absolutely not have time to go through it, sorry. You can just read about in the paper. Different kind of information, like you can use it for debugging purposes and stuff like that. It's pretty much similar to this project. But it's way less than that because I'm interested in some subpart and subset. In conclusion, in NUMA systems, we need to schedule threads and memory. The information about the system layout and the workloads is exported to user space. Most of the information that you need is available there. The rest of the information is available through hardware counters, for example. You can use the tools to trace kernel as well if you want additional information or something like that. But I find that for me, the data that Linux provides you on user level and the opportunities it provides on user level is sufficient. If not, I just use hardware counters for that. Clavis is an open source application written in C, leverages opportunities for user level scheduling, provided in Linux to test different scheduling algorithms on user level. So you can use it. Clavis means E in Latin, so it's just, I decided to name it that way because it helped me to unlock the disadvantages and advantages of the scheduling algorithms that I used in my research. This is the page for the source code. I uploaded it yesterday. Maybe it's not as good as I would wish it to, but you'll be able to get it right. Yes, you're all hackers here, so that's fine. And if you're interested, tomorrow I have a presentation in Portland. I have a paper accepted to use in semi-technical conference there. It's about the algorithm. So it's about this problem that I solved with the scheduler. If you're interested, you can read it. It will be available through using proceedings there. And that's it. We have some time for questions still. So if you have any questions, I would be happy to answer them. Yeah.
Could you describe a real-world application that would benefit from these techniques? A
Right.
machine that runs on them? Like describe the relationship between the machine and how the software was able to
Right.
maximize the machine?
So first of all, about machines, I use only real machine. I don't use simulation in any way, anything like that. I don't really like it. So some people use it, I don't. Everything here is on the real servers that you can buy from Dell in this case. We have some servers from HP as well, but it's all real stuff, real deal. Linux is just plain. I use Linux Gentoo because I like it, but you can use any Linux. All of these opportunities that will be provided by any Linux distribution because this is really distribution. Not related. You can get it from me. The programs that I use, particularly my research, is being considered targeted at CPU-based applications, and usually these applications they are scientific ones. or in HPC domain, high performance computing domain. In order to test the efficiency, I usually use the benchmarks, for example, from spec, spec and PI. I also use the workload from LAMP stack, so Linux, Apache, MySQL, and PHP. So this is like, open source platform right there. But I'm mostly considering CPU intensive I can record. So if you have some kind of site that's CPU intensive content, for example, from PHP, auction site or something like that, if it will require a lot of CPU time, my algorithms can probably help. Most of the time, though, like in web, the bottleneck there is not really a contention for memory resources. The bottleneck is just waiting for the data to come. It's transactional workload, for example, with web. So because of that, my algorithm won't help in this case. I only target CPU-intensive applications that compete for memory hierarchy of machines. But it's benchmarks are representative for this domain, so that's why they're created for example, this stack. We're paying money for that. So yeah.
Have you, and I'm sure you have, how would you deal with applications where you have more where it basically has a lot of threads and a lot of memory?
Okay.
I think like a big application, a database server, there are more threads than you typically have on a single socket. So you're basically in a situation where you need multiple nodes in play.
Nothing much I can do in this case. So if they have more threads than the number of cores in the socket, and they're all CPU intensive, I will not schedule them on the same core because the number of competition will be just extreme. What I will do is that I will try to schedule them on a small number of sockets as possible. So that, for example, if you have, for example, the 4 cores per socket and you have an application with 8 threads and all of them CPU intensive, they share the same memory footprint, I will try to schedule them on 2 sockets if it's possible. And then I will use some kind of technique to migrate only hot pages around, not entire, because for multi-thread application, the migration of the entire memory footprint is just insane. There's no, if you, for example, have 4 threads of this application on one socket and 4 threads on another, you will just, you try to migrate them all the time, like all of the memory is just infeasible. You will use some kind of fine-grained migration, like, for example, you provide a core with, this second mode of performance execution, you just want to migrate only hot pages. So usually this multi-thread application, they have certain, within this memory footprint, they have certain local memory to work on. So because of that, with this hot pages technique, you will just migrate on the pages that are supposedly will use. There will certain page bounds in between the nodes, but it won't be as much. And also another thing, which is sort of common knowledge in systems field, is that contention effects between the threads, they are more important than sharing effects. So for example, if you have multi-thread application, if they're all using memory extensively, and if you place them on the same memory node, it is quite possible that the contention effects will outweigh sharing. Because they will also compete for, they will all access their own common memory, but they will also compete for that because the resources are shared sometimes. So because of that, a lot of times it's more important to schedule them apart. But people want multi-thread applications to be run on the same machine. As of yet, we cannot tell online. So we can tell the degree of contention for resources, but we cannot tell the degree in which applications share the resources. On Halen, there are some contracts that will sort of like that allow you to do that in a way, but it's not precise enough. So we are waiting for the next sort of processors, maybe in their hardware performance units, there will be contracts that will allow us to estimate what is the degree of the sharing effects. If we will have this data, then we will be able to tell whether we want to cluster them together, all these applications, or we want to spread them apart, because in the case where contention will outweigh sharing. But as of yet, since we don't know that, we're still assuming that we don't want to migrate memory, we don't want to bounce some pages, so we want to schedule application on as few memory sockets as possible, but by preserving load balancing. So I would just schedule them on 2 sockets in this case, for example, with 8